Welcome everyone, and welcome to the 6th lecture on this digital image processing of remote sensing data. And in this particular discussion we will focus mainly on color representations and transformations. But before I proceed, this is very interesting that basically colors do not matter. Though I am making a little bold statement, the colors do not matter really in remote sensing. What matters the pixel value, digital number of an image. But in order to represent or in order to display images or get their printouts, we use colors, and therefore colors becomes equally important in digital image processing as well as in remote sensing. Also, we exploit the fundamental properties of colors, their combinations, primary colors, additive colors, secondary colors for different types of, for different purposes. As we know that primary colors we use while displaying something on computer screen or maybe through the projection systems and other things. Whereas the secondary colors like cyan, magenta, yellow and black we use for printing devices. So, there are various applications of this. However, in digital image processing we can exploit various aspects of colors and can perform color transformation and exploit the images of different spatial resolutions and different band images and can merge or fuse the images. So, in this particular discussion we are going to see all these things in much more detail. As we know that there are various characteristics. So, the three important characteristics of colors are hue, that is the basically color, then brightness, also we call that the luminance of the object, and then the third one is the saturation, the like for example blue sky. So, these three characteristics are very important. Also from one if later on I will be showing one color cube in which we can perform transformations from one plane of colors to another, and there these fundamental characteristics hue, brightness and saturation will play major roles. So, these are the very important things to remember. Now, in the previous lecture I have discussed in detail about the visible part of EM spectrum, and this is how different colors will respond. So, in the lower wavelengths that we call as blue spectrum, as we can see here that here the blue will have the maximum reflection, whereas in the green part of this thing we will have, but see in the cyan part hardly any reflection. But then in the later part of EM spectrum, that means towards the longer wavelengths, now we are getting the red color. So, all these three primary colors blue, green and red are present, and their reflectivity in relative sensitivity here is plotted, is exploited in digital image processing extensively. This is the color cube which I have just mentioned few seconds before. In the far behind there is the corner, this is which in this demonstration we assign a black color, and all values we keep here 0 0 0. So, it is a 3 because it is a 3-dimensional. So, there are 3 axes are there, and that is why there are 3 values have been mentioned. So, when all values, that means if we think in red, green and blue in that sense, then when all values red, green and blues are 0, then we get the black color. And when all values in this here, the scale is between 0 to white, when all values are 1, all these 3 axes red, green and blue, then white, and this is what is shown here. The red axis is here, the blue axis is here and the green axis is here. And like in case of red axis, it is the extreme, and here so one is 0, the first one is red and then second one is green, third one is blue, and both of these two color component or role of these two colors at this corner are 0. No role is there. Similarly for green, whereas the red is 0, green is 1, the maximum, and then blue is 0, whereas in case of blue 0 0 1. And then secondary colors, which is the cyan color will occupy the other remaining corners of this cube. So, 2 corners have been consumed by black and white, other 3 corners have been consumed by red, blue and green. Now 3 more corners of this cube left, that is one is cyan. So, there cyan is the secondary color and therefore, it is made from blue and green. So, these two are playing very important role. When they are having the full strength, then you get the cyan color. In case of magenta color, you get only red and blue, and green is 0 and it is the secondary color. So, it is formed here and located in this representation on this corner. And the third one is the yellow, which is 110, that means it is having red color component, it is having green color component and no blue component whatsoever, and it makes the, so all three primary colors, all 3 secondary colors and 2 extreme colors which makes your grayscale are located here on all 8 different corners. So, if you assume a line between black to white diagonally this axis, then the gray image will be formed if we exploit that one. But if we exploit more than 2 colors, then there is going to be a plane which will touch all these 3 corners and the image will be projected on it. So, for understanding of colors and color transformation especially, understanding of this cube, which is very simple one, has to be in real sense and very much required. Now, if we take out a cone out of a solid cone out of this cube which is shown here, then on the base of this cone all colors, all 7 colors will be present here, and that we call as hue. And the brightness, because the black is the darkest, white is the brightest, so the brightness will be represented by a axis which is nothing but the height of this cone. So, that is why here it is black is shown, white is shown. And then saturation is about these individual flakes which are shown here, that makes, so in the inside you do not have saturation, but as you go towards the corner of this color cube, the saturation increases, and at the extreme corners it reaches to the maximum. No other colors in case of primary colors play any role, whereas in case of secondary colors only 2 main colors will play major role. So, after understanding this 3D cube of color space, now I have taken out as a cone, and understanding of this cone will make our understanding much better about the color space and particularly the transformation, which we are going to talk little later. So, as we know that color space, which these 3 discs we have been shown since childhood, but very briefly I will go through that. The simplest color space which was told to us, the axis or the corners of color cube are red, green, blue. Advantage is it is simple, and these are also primary one. Now, when we go for mixing of colors, then the primary colors are red, green, blue, and when you mix like red and green, you get yellow. When you mix red and blue, you get the cyan or magenta, and then you get the cyan as well. So, the complementary colors are red and cyan, green and magenta, blue and that thing, and when these all colors are getting mixed, then you are getting the white color. So, this is what white color can also be defined. Then the red and the cyan you add, then red plus B plus green, and then it makes white. So, here you can see that the red color, then the cyan color is there, cyan color is here, and then red again you mix with blue and green, that makes the white one. The color additions are also exploited in digital image processing. especially in color transformations, like when we add R and red means red and green, we get yellow, and red and blue we get magenta, and green and blue we get cyan. Very interestingly, when we go for SAR interferometry processing using the radar data, there the fringes will also be generated, and which are also in these colors, and there we count the fringes in order to estimate the deformations. So the colors are also become very important even in case of SAR interferometry or radar remote sensing or microwave remote sensing. So colors are not only important in case of visible or infrared, but also in radar remote sensing. So both active and passive remote sensing processing, that means digital image processing of these data sets, colors play very important role. Now let us discuss little bit about the subtractive color mixing. That is it is also, we say, pigment, because these are the colors which use for printing. So these are the primary colors in this one, though we call them subtractive. Under the subtractive color scheme we call them as primary, but in normal understanding we say the secondary colors cyan, magenta, yellow, because they are made from two other primary colors, whereas primary colors cannot be made from these things, or more close colors can be generated. So the complementary colors like red and cyan, green and magenta, and blue and yellow, all these are shown here. And again, when you mix all these, like in case of additive color scheme, you get white in the center, here you get the black in the center. There are other ways of representing color space, and one way is the Newton color cycle. You might remember a Newton disk which was in our 7th, 8th class physics or science practicals, which was when this disk is rotated at relatively a higher speed, we see white color. In order to demonstrate that it is made, all white color is made from these 7 colors. So that is why the one way of representing or predicting the color mixing is using this concept. Now hue, saturation and your brightness, they are very important here. So and that is why the CM by K, that the cyan, magenta, yellow and black are there. As I have already mentioned, these are used for printing, and these are the subtractive color mixing. Their axes are important. The 3 axes are there: cyan, magenta, yellow and black is also used, so that we don't have to mix all these 3 in order to create black, saves the resources. The color space from we can convert. What I mean is that if you are having a color image, if you are having a color image which is made from RGB, 3 colors, red, green, blue, you can split that into 3 other color components, as I have been mentioning, that intensity, or you can call as brightness, hue and saturation. So this is splitting, and inverse is, or backward transformation is also possible. So we can also transform back to RGB space as well. That means we are basically changing the plane within a cube, and within that color space, as I have discussed in the beginning. So this is very important, that conversions are possible, and we do it when we go for color transformations in digital image processing. So you can generate different colors using these kind of simple equations, and like black also minimum C, minimum M and minimum Y, you can get these color. Now if we compare between these 2 major schemes, one is primary, secondary, or additive or subtractive color scheme, like RGB additive color scheme, primary parameters are red, green, blue, and used for, of course, display, and then easy but not wasting bandwidth here. Whereas CM by K is a subtractive color scheme. The members are parameters are cyan, magenta, yellow, black, mainly used for printing. Here it is used for display and working in the pigment or mixing and printing as well. Now let us come to the real color transformation kind of thing, but before that, color composites. One color composites, we are now familiar with the false color composites, where we assign different color channels to different bands, and ultimately we end up with a RGB color, an image which falls in the RGB color space. That means a plane which will touch all these three corners. So your image will be projected on that. So red band if we are approaching for, instead of false color, if we approach for the real color or near real color. I also told in previous classes that using satellite data, it is near impossible to create a true color image what we see through aircrafts, and the same color image we can generate through mixing of colors or this thing. So whatever the we even mention a real color composite, it is near real color, it is not truly color, because we will be exploiting infrared, and we know that by invisible light or our eyes are not sensitive. So when what we see through aircrafts, that kind of image cannot be seen through the satellite images by mixing of any kind of bands. Anyway, so the red band on red, when we assign red band, that part of later part of EM spectrum in the visible section, so that part as discussed earlier is called red band. Then green band on green and blue and blue. So simple color composition, and that makes the real color composition. That is possible when you are having narrow bands and relatively more number of bands. So in case of Landsat MSS, such a composites are not possible, but in case of OLI series like Landsat or in other cases when we will have the hyperspectral, then probably all these things are possible. So narrow bands are required, more number of bands are required in order to create near real color composites, and this is the output from that one, that red band on red, green and green, blue and blue, and this is what you see here. Near real color composite image, but generally for better interpretations we prefer false color composite, because vegetation here is coming quite dark, and therefore it becomes very difficult, not really in green, in true color images or near color, real color images, the vegetation should cover green, but it is not, and there the chlorophyll content is reflected differently in infrared channels. So there the distinction between various objects including vegetation becomes much easier in false color than real color, but still for some certain applications maybe a real color or true color images or composites might be required. One other possibility is red band on red and green band on green, blue is so that you may end up a different kind of representation or a color composite. Now let us come to the color transformation, and I will show you the real how it is done, that if you are having images, two sets of images, one has come like panchromatic or black and white image, might be having higher spatial resolution, and there might be another image, another sensor which might be providing multispectral images but at lower spatial resolution. And the example is shown here in this flow chart, that in the real example what we have done, we have taken IRS1C pan data, which is a panchromatic black and white data here, and IRS1C list 3 which is false color or is multispectral data. So the spatial resolution here is, in case of IRS1C pan, is 5.6 meter, whereas in case of list 3 the spatial resolution is 23 meter. So how color space can be exploited to create a new product which is merged or fused product. Fused product in sense that in this output image will exploit both the best of spatial resolution and best of spectral resolution. That means it will have a higher spatial resolution but in colors, whereas separately here we are having higher spatial resolution but in black and white, here we are having multispectral or colored image but lower spatial resolution. The output will have both, advantages of both. How we achieve? A very simple way of doing this thing, that first image to image registration is required. In later sections of this course we will be discussing the georeferencing section, which is a very common technique even in GIS as well as in remote sensing digital image processing. So, very much required. So, first image to image registration, that means the pen image and the list 3 image should fit or they stack together very nicely. If there is a mismatch, then the output will not be very sharp. So, also some people get the pen sharp images. For fused images or merged images, they also call pen sharp images. Pen sharp means they are exploiting the higher spatial resolution data which is available with pen chromatic sensor, and using and mixing or merging that data with multispectral data which is having relatively low spatial resolution. So, first step in is image to image registration. Then this registered pen image continued here, whereas the registered color composite or false color composite is splitted into 3 components: red, green, blue. That plane is projected to IHS as also mentioned here. And when this splitting is done, now 3 channels, initially you had red, green, blue, you have created new 3 channels which is intensity, hue and saturation. Remember that base of that or the cone which we took out through the 3D cube as well. Now here this intensity image, hue image and saturation image. So after splitting RGB to IHS, we get 3 images: intensity, hue and saturation. The pen images which is already now registered, pen image which is having higher spatial resolution, be replaced with the intensity image, because this is still carrying low resolution, that is in this example 23.5 meter resolution. So, we drop this one, therefore, there is no continuity, and we continue with the pen image of higher resolution, and then we go for reverse transformation or backward transformation. That means again from IHS plane to RGB plane. And after once we perform this, then we get an output which is having higher spatial resolution than earlier, and same time it is having the colors which are coming from multispectral data. So, 2 sensors data, in this case these were both on the same satellite, but one can exploit. I will be showing an example where one map and one satellite image can also be merged, can also be fused, and you can create a new product. So, playing with colors in digital image processing is very, very important. Though in the beginning I said if you start looking individual band of an image, then colors do not have any meaning because the pixel values carries the meaning. But here we are putting them into color space, bringing them into color space and trying to exploit the color or the color cube and the cone and for our own benefits. So, let us see the real example. As I have been mentioning, this is a cone, a little bit differently it is shown here, that on one end you are having red on this circle which is nothing but the base of the cone, the apex of the cone is here, and here you will have the highest intensity, here you will have the lowest intensity. Opposite to red you will have cyan color, if you opposite to green you are having magenta color, and opposite to blue you are having yellow color. So, this radius is nothing but the saturation, the perimeter showing the colors or hue we call them, and intensity axis is black to white, which is from the base of the cone, center of the base of the cone to the apex of the cone, and this is how we exploit this one. Now the real example, as I have been mentioning, IRS 1C pen 5.8 meter resolution taken of 11th February 1997, and this area is a part of NCR region, Delhi region. You see a very sharp image, but it is in black and white, whereas you see a colored image or false color image from list 3 IRS list 3 image, which is 23.5 meter, but not as sharp as here, not as sharp the pen is this list 3. So it is having one quality, list 3 is having one quality, that it is in colors, and whereas the pen, though it is in black and white, but it is sharp, it is having higher spatial resolution. So the main purpose here is to use the best quality of both and create a new product, and this is how the product looks, which is now at 5.8 meter resolution and colors as well. So simple pen image didn't have the colors, and your list 3 didn't have the resolution but had the colors, whereas this merged image or fused image or pen sharp image is having both. It is having color and higher spatial resolution. So just exploiting the color space, playing little within the digital image processing, with digital image processing softwares, we can create new products, and this is what people have been doing. Now these products, I will show you some zoomed area of all 3 images together, that here this is the list 3 image, this is pen image, higher spatial resolution, lower spatial resolution, but this is multispectral, this is panchromatic. The best quality of both is exploited, and this is what you see. Though the colors in typical false color composites are not appearing in the image C, which is pen sharped or merged image, but see the distinction, and this is the Delhi golf course area where individual these holes can be identified very easily as compared to black and white image or even false color image having relatively lower spatial resolution. So this is how the merging can be done, exploiting color space. Now let me take another example where in this case one colored map was used, and the purpose was little different here, but the same color space was exploited little differently, and this is what the beauty here is like this, that this was a print, as you can see even the folding seams which are visible here. So this was a print but in color. So this was scanned, and then once you scan an image or a map which is a colored map, then you get basically a color image, and you can handle as a colored image. So I handled that one as a colored image, and we had a very high, relatively higher resolution data, list 3, band 3 spatially, that because the target was to see the vegetation, and band 3 is the near infrared part of EM spectrum for the this list 3 sensors. So the main purpose to see the water body as well as vegetation. So especially the band 3 was chosen here. Though list 3 color composites can be made, but here now we are doing a little differently, that we are using colors here of this Dal Lake map, which is a Survey of India map at a very large scale, but it is age wise or date when it was surveyed was in 1968, but in this is 1998. So 30 years time difference. So here instead of like in previous example, here now we want to see how things have changes around the lake, especially in the lake body, the water body, between these 30 years. And this is how we exploited that. This is the output from that, and this is the black and white representation of the map. We use as a we split it one, and we used as intensity map, and then you are having one more channel, and the same channel is repeated here. So instead of having 3 RGB, now we are having 2 and one is being repeated, and the output, what output is showing? Very interestingly, it is showing the red color. These are the all changes which has occurred between these 30 years. The map belongs to 1968, the satellite image belongs to 1998. So there is a 30 years time reference. In between, the lot of encroachment has occurred on the edges or perimeter of the lake. Even in the these waterways also were choked by growth of vegetation, and that is very much reflected here. But the first requirement is registration. So map should be registered first with the image. Then instead of having 3 channels, one can have even 2 channels. One is map, another one is satellite image, and both are single, not colored, but splitted into 3 color, 3 intensity hue and saturation. Intensity image was taken here, band 3 was taken here, band 3 was repeated, and then you get this kind of output. So doing like this, you can create a new product which is telling how things have changed. So the color space can also be exploited, is being exploited extensively in change detection studies. Whether these changes are man-made or natural, whatever is, because since 1972 now we are having data, satellite data. So if we want to see the changes what has happened in last 43 years roughly or 45 years, and we get the old image, no matter how what was the spatial resolution of Landsat MS and what is the spatial resolution of say Landsat OLI series, that is Landsat 8 images. There is a change now spatial resolution, but still two different spatial resolution images with exploiting color space, color cube can be merged together, and a change detection image which will tell you very distinctly how things have changed. Another example, another part of this zoomed part is shown here, that the lake, this is the image, and this red all are showing here the vegetation has grown in last 30 years. So this is how one can exploit color space in change detection studies as well. One or two more examples from earthquake studies I will show you, very simple. Here now the sensor is same but 2 different dates, and both images belongs to the IRS pen. So 5.8 meter data, 5.8 meter data, and this is just 5 days time difference, and in between earthquake has occurred. So like this is example from Chamoli earthquake. So Chamoli earthquake occurred on 29th March 99. The change, what do you see here? After 5 days another image was acquired. So the same way we can exploit, we can because in order to create a color composite we need 3 colors. So one this image was repeated twice, this one given the red color, and the output you see here is that whatever the changes which has occurred in terms of reflection induced by an earthquake, that is in this case Chamoli earthquake, can be seen through red color. And if some white spots are there, that means you are saying that no change has occurred, as you can see very well, that there were already some signs of some slope failure, and then in between the earthquake has occurred. After that an image was acquired, and when you create this pseudo color transform image, not a truly false color composite or a map merged image kind of thing, this is pseudo color, a new name was given by us, that is a pseudo color image can be created which will tell you where changes have occurred between these 2 dates. And in this case the dates are very close. In case of like Dal Lake study, the dates time difference was of 30 years, here is only of 5 days. What I am trying to say that the color space can be exploited to maximum for different type of studies. It depends on for what you are going to exploit, and use them and create a new product. Another example from the same earthquake, same sensor, this is pre, this is post. When you create a pseudo color transform image, you end up with like this. So large part here is also in white. That means there were already some landslide. Due to this earthquake has induced further landslide, new landslide have come, and so this was not there, though there were signs of early failure, but slow failure. Now it has enlarged. So these landslides have enlarged, and the new one has come. That is what it. So this shows a very a nice application of color space, exploiting the or creating a new product which is telling about the changes which has occurred in just between 5 days. Similarly, in another example of instead of a very high resolution, if you go for relatively low resolution satellite data which is covering a very large area, and again the time difference is of 5 years instead of 30 years or 5 days. Here time difference is roughly 5 years, and you can create a change detection map. Not only that, the orientation of landslide can tell you some other story, why they are aligned, because of some tectonic feature which is a geological fault or thrust. Similarly, in case of Bhuj earthquake, where we had a very high resolution data, again for individual houses one can exploit color space, color transformation techniques, and can create products which will very quickly will tell you where changes have occurred. So color space or color transformation techniques are very useful for change detection studies. One more example, and the last example in this color transformation is that here instead of like a pen, we had this is the list 3 data, and list 3 itself is a multispectral data. But we wanted to see only the changes in the water and in moisture, and the best channel is infrared channel. So we exploited infrared channel the same way as in case of the pen in case of Chamoli earthquake, but here instead of landslide our focus was on liquefaction, which is another co-seismic phenomena which occurs during an earthquake event. And so for pre-earthquake image which was of 4th January 2001, you might be remembering the Bhuj earthquake which occurred on 26 January 2001. So roughly 22 days before the earthquake, there were one recording by the IRS Bundy, list 3 image was there. Then after the earthquake on 29th January, another image was acquired of the same area. Luckily both images, that means the 4th January image and 29th January 2001 images, both were completely cloud free. So the best thing is just first to do as good as image to image registration as possible, which is not very difficult to perform. And once that is done, then the color space plays very important. So what we did, we assigned 2 channels for pre-earthquake and 1 channel for post-earthquake. That is the red channel to the poster. And when you do it like this, you get this kind of product which you can see here, that the water bodies which appeared, which is a liquefaction as a co-seismic during an earthquake, and they remain on the surface for some time and were unbiasedly recorded by the satellite. So all these red areas are showing the changes which has occurred between these 2 dates, one, and changes specifically related with water. Either moisture has increased or fresh water bodies appeared. So there were some drains even developed for some time because of liquefaction. The groundwater came on the surface and flown for some distance on the surface in that particular area, which was mostly a large part was affected due to liquefaction. So depending on the application, one can really exploit such things. Another example, altogether a different way of exploiting is, this is a list 3 image of Bhagirathi river valley of Himalaya. Bhagirathi is a tributary of Ganges, and this is list 3 image, and remember these azimuth and sun elevation angle of 1998. Now this is a shader relief model derived from a digital elevation model, which we have discussed extensively in introduction to GIS course. And here just recall the azimuth angle. The azimuth angle in this case is 163.3 degree. It is just adding 180 degree, and the sun azimuth is here. Now this image, this product which is a generated from digital elevation model, can we use as an intensity image. And if we split this image, which is a RGB image, a false color composite image, into 3 channels, intensity and hue saturation, hue of list 3 is dropped, and that is replaced by intensity of this one, and then so intensity image from this one is dropped, this is replaced by intensity image, this is the shadow relief model, and rest hue and saturation continues, and in a inverse or backward transformation you end up with this. The purpose here was, if you see here, you might feel, because of false topographic perception phenomena, you might see the river is flowing on the ridge, but actually river should flow in the valley. But because of certain illumination arrangements and the geometry of the satellite and solar illumination, you feel that river is, and this phenomena we call as false topographic perception phenomena. So in order to get rid of that phenomena, one can exploit and can create a new product in which river is flowing in the valley, which is and giving you correct perception, and the same time you are having colored image. Whereas your shadow relief model, though looks quite close to the your satellite image, but does not have the colors like your image. So a new exploitation of color space. There are unlimited possibilities with color space. As per requirements of the application, one can evolve a new technique by splitting and then reverse transformation, dropping some channel, dropping intensity image or some other image, and can create a new product. So this brings to the end of this color space and transformation. Thank you very much.